Let's put this all together to talk about how to graph a function y equals f of x. First of all, you're going to identify the domain and the region of interest. You're going to exploit symmetry if possible, looking for even and odd functions. You'll calculate the first and second derivatives, if possible. Sometimes the second derivatives are difficult to find. We'll find the critical points and possible inflection points. That is, we'll look at where the first derivative is 0 or defined, and where the second derivative is 0 or undefined. We'll find intervals of increasing and decreasing regions and concavity up and down. We'll identify extreme values and inflection points. We'll look at asymptotes and end behavior. We'll find any intercepts, and finally we will plot our function. Let's do this example. F of x equals x cubed divided by 3 minus 400x. The domain for this function, it doesn't look like there's any limitation, so my domain will be negative infinity to infinity. To look at symmetry, I plug in negative x for f of x, and when I do that, I find that the function f of negative x is equal to negative f of x. That means this is an odd function. It will be symmetric about the origin. Now let's calculate my derivatives. Once I find my first derivative and my second derivative, I'm going to use those to find my critical points. That is, I'm going to set those equal to 0 and solve for x. I find that my critical points, when I set that equal to 0 and I factor, that x can be 20 or negative 20. A possible inflection point is when the second derivative 2x is equal to 0, and that occurs when x is equal to 0. The next thing I'm going to do is take those critical points, put them on a number line, and look at when I have increasing and decreasing functions. So when I pick three test points, negative 100, 0, and 100, and plug those into my derivative, I find that I have an increasing function from negative infinity to negative 20, from 20 to infinity, and a decreasing function between negative 20 and 20. The next thing I do is look at that possible point of inflection when f double prime at 0 equals 0. And if I look to the left of that, I see that f double prime is negative, and to the right of that point, f double prime is positive. Therefore, to the left of 0, I have a concave down function, and to the right, I have a concave up function. I can then find my extreme values and inflection points. I see that because I have a increasing to a decreasing function at negative 20, I have a maximum at that point. At positive 20, I have a decreasing function switching to an increasing function, which means there is a minimum at positive 20. At 0, I can check for an inflection point, and f double prime changes sign at that point 0, therefore that means that is an inflection point. If I look at my asymptotes, I don't think I have any asymptotes, but I can look at end behavior. The limit as x goes to infinity of x cubed divided by 3 minus 400x, that's equal to positive infinity. And if I take that same limit but I let x go to negative infinity, I get negative infinity. The final thing I'm going to do is find an x or y intercept to kind of be able to place this graph somewhere on the xy coordinate system. To find my x and y intercepts, I first let x equal to 0 and I solve for y. When I plug 0 in for f of x, I get that y is equal to 0. To solve for when y is equal to 0, I set 0 equals x cubed divided by 3 minus 400x. I factor out an x, and I see that I get either x equals 0 or x is equal to plus or minus the square root of 1200, which is approximately 34.6. We now have all of our pieces together to graph. So I know the point 0, 0 is a point of inflection. I know I have a maximum at x equals negative 20. If I plug in negative 20 into my function, I get about 5,333. If I plug f of 20 in, which I know is a local min, I get negative 5,333. I've got those 2 points. I know it crosses the x-axis at negative 34.6 and positive 34.6. I know the end behavior as x goes to infinity is infinity, and I know as x goes to negative infinity, it's negative infinity. I also check to see that my function is concave down from negative infinity to 0 and concave up from 0 to positive infinity. Therefore, this graph matches what I've found using calculus.